Hello everyone. In this video we'll be talking about performance navigation, accuracy, integrity, and continuity that are defined within the navigation specification. Well, let's say we have here a runway, okay? This is our runway. Imagine here we have, I don't know, some Papa, Delta, Romeo airspaces. We are not supposed to violate. We have an approach, right, going like this and down to the runway. I don't want to specify more things. Well, so imagine we define here some lateral error, right? Our mean values are somewhere, right, around the desired path, but we have some errors. Well, that error, which is, as you already know, the total system error, can be modeled as a normal with zero mean and standard deviation sigma total system error. Imagine this is our zero mean, right? The desired track, and we display a normal distribution like this, right? Let me also go here, right, to do it. In a normal distribution, we know, right, some containers. This 2 sigma error contains, let me just, right, this 2 sigma contains 95% of the cases. Just 5% of the cases will go right or left these containers. And if we double the container, the say 4 sigma one, then the area under the whole curve is covering now 99.99% of the cases. So here we can define in our route a similar thing, right? A 2 sigma of the total sigma error and a 2 sigma of the total sigma error to one side and the other. Well, we define accuracy as follows. Aircraft, when flying this route, should be 95% of the time within the 2 sigma container, right? Meaning that if I specify a required navigation performance of x, being x nautical miles, a distance, x has to be equal to 2 sigma of the total system error. Okay, this is this x I am defining. To one side, to the left, or to the right, I don't care, right? There's this symmetry. So when defining the navigation specification, required navigation performance x, it can be 5, 4, 3, 2, 1. We will see this, right? We are saying that the total system error has to be x over 2. Right? This is the total system error, the standard deviation we can cope with. We need to define our system to fulfill this criteria. When it comes to continuity of the signal, it means that the probability of the aircraft being outside the 4 sigma container, I didn't mention that, but this big guy is a 4 sigma container, right? So the probability of being outside this one but sending some sort of alert is 10 to the power of minus 4 per flight hour. In other words, once every 10,000 flight hours. That has to do with continuity of the signal. And when it comes to integrity, the definition is similar, but in this case, this has to do with the probability of the aircraft being outside, again, outside the 4 sigma container. So outside the 4 sigma container, this is the same, outside the 4 sigma container, and this being 10 to the power of minus 5 per flight hour, but in this case without alert. So once every 100,000 flight hours we would be outside the 4 sigma container without having an alert. In the case of continuity, is once every 10,000 flight hours, but in this case providing the alert, right? So one thing is continuity, in which you are still, the system is still working, but for some reason we are beyond what we should be, where we should be. When it comes to integrity, the system is not working, and on top of that, I don't know, right? So it's another failure on top of the other. So thanks very much for your attention.